If you remember, I was coding on the antivirus program and we had some trouble because it was able to differentiate between directories and regular files, but it somehow thought that regular files in some cases were special files, so it didn't show in the database. And the solution was to rewrite some parts of that check. So this is how it looks now. I created a new variable called dtype, and dtype is an unsigned char pointer. So I pointed that towards P2, which is the current position in the buffer, plus reclan, which is the number of bytes for this file. So basically P2 plus reclan means we go to the next file. But then I do -1, so I go to the last variable inside of that structure, and I point this towards that. And then I do reference this pointer, and I do a regular if check if it's a regular file or if it's a directory. So that's how I was able to fix this bug. And now if we run the program, and that is the only thing, the only code I have added since you last saw the code. So if we do make clean and we make this again and we run bird flu on, let's say, /tmp, all the elf binaries show up, including those who's in well, other folders, deeply nested, etc. So this works perfectly this far. So now we are able to find the executable files on the system and create a database with those. What is the logical next step? Well, that is to check all those files for viruses and log somehow inside of the database if they have been scanned and when they were scanned. And I think we can use the Unix time system, which is the number of seconds that has passed since the 1st of January in 1970. And I did use that in an older episode. I can't really remember which one, and I don't remember how I got the timestamp. So let's see how we can figure that out. Well, let's run something which does use that. We can do the time command, because the time command runs the command afterwards and counts how many seconds and fractions of a second that has passed while running that command. So if we run this and we run it inside of strace, and then we pipe the output to a file, write. Time is not an executable. It is a function built into the bash shell, which complicates things a little bit. Maybe we can run date instead. Let's try it. I didn't want that output, I want this. And then we open the file and we try to figure out where the system call happens. So let's see. This is where we print the things. And we run a couple of things. Let's see which seems to be the most promising. What is this? iButes. Okay, it's from the command on the line above. And this is just a statx call, which is basically checking a file. Let's open this again. Let's see if something looks like the right thing. Get our limit. Parsec. Set to. We open a bunch of files, map some memory. And more of the same. What if we were to run something like, if we launch another bash and we run the command time ls. Is it possible to run it like this? Seems like. Alright. So let's see. Where do we print the output? What if we search for write to, let's see, standard input output errors 1, write and then anything and then a 1. Okay. So here we print the different timestamps. Then we should, what about this? Get our usage. Let's see what that is. Get resource usage. Okay, so they are using this syscall in order to count the seconds that pass when running the command. What about this one? Clock get time. clock and time functions. That sounds like the real thing. So what do we have? We have three functions: get, res, get time, and set time. So I guess we're going to use this get time, and it takes a clock ID and a struct time spec. What is a clock ID? The clock ID argument is the identifier of the particular clock on which to act. A clock may be system-wide and hence visible for all processes, or per process if it measures time only within a single process. Okay, so we want to use this clock real time. So we include time.h and we use clock get time. And we need to construct a struct time spec. I think we can do that. So let's see. Let's create a function which we'll call Unix time. So it'll return a int64, I guess. Or no, int8 is what no, int64. Unix time and no arguments. So this function should get the current timestamp in seconds. Alright, so let's write this function. We have an int64, Unix time, and we need a struct time spec. And we need to call clock get time with this clock and the time spec. Seems almost too easy. Real time, monotonic, dynamic clocks. And I want to see how this struct time spec works. So let's see. Okay. This is pretty self-explanatory, isn't it? We get the seconds and we get the nsec. I suppose that is nanoseconds. So we are interested in TV sec. And let's create an integer for the return value. And how do we know if it failed or not? I'm not sure if it practically can fail, but let's see what the return value should be. Return 0 for success, all right? So if ret, then we return 0 as an error. Otherwise, we should have something in the time spec, so we should be able to return it. And I am only interested in the TV seconds. We don't need that kind of precision. Okay, so let's create an int 64 time, and we set time equal to Unix time. And if we have a time, we return it. No, we do not return it, we print it. And this will be an LU, I guess. Or is it an LLU? I don't use these 64-bit variables very much. Alright, so let's see. Time. And otherwise, we will just print error. And then we quit. Something like this. Let's see. Oh, we need to add the include as well. So it should be time.h. Simple enough. Okay, compile without any errors or warnings. Let's see if it runs. Yeah, we got something. And if we run this consecutively, you see that we have 66 at the end, 67, 68. So it works. It does actually work. All right, so now we are able to get a proper timestamp. And let's create a variable type for these kinds of timestamps. So let's type def unsigned long int to, what should we call it? Timestamp. Maybe with a capital T. And let's change the signature so we don't return an int64, but we return a timestamp. And let's not forget to alter this timestamp, and this should be fine, I guess, but let's do it the proper way, like so. Alright, still works. So, okay, what's the next step? We need to alter our structure a little bit, because currently an entry is just a file type, directory, and a file. It should also be a timestamp when last scanned. So let's call this last scanned. And if it's equal to 0, it has never been scanned. And I believe we have, do we have a structure function for the entry? Maybe not. So how do we produce entries? Let's see. Entry E inside of add directory. Right, so we create it manually inside of here. So we want to zero out the timestamp last scan, and I probably zeroed out the entire structure, but it's also good to do this just to well, make sure that we have all the different parts of it. It makes the readability better, right? Okay, so let's see. Maybe it's time to produce some logs and stuff. We can create an alias, a macro. Let's call it log, and it takes an X. Maybe we take a format string and args. And then we simply do a printf with a format string and the args. And this will fail if we do not have any args, but that's good enough because we should always have both a format string and some kind of argument. Right. So maybe we should create some function which contains all these different steps. Some kind of preparation function. Let's call it prepare. And we don't need any arguments. I don't think we do. Let's see how our code looks currently. Make database. Directory. Well, we give it a command line argument, but I don't think we should, because we will always use slash as our directory, because we do want to scan the entire disk, right? Well, we can basically just copy all this stuff. We can remove this and this, and then we create this function, void prepare. And we'll lift everything over here into here. And let's add some logs. Make database, add directory. this will just be a slash. And let's log something like well, what is the first step? It's enumerating all the files on disk. So let's tell that. Enumerating file system. Maybe we should add one thing to our macro, and that is to flush the buffer. So we can print without ending in a new line. And maybe we can add a nicer looking user interface later on. So we add this directory like so. Let's add something like done. And maybe we tell how many files we got. Enumerating file system found %d files. And this is the db.num. And this should be dot because it's a pointer. And we don't need to. I think we can overwrite the old pointer. And what is the next step? That is filtering filtering the non-executables. Like so, and we set db equal to this instead. I think we can do that. Let's remove this for now. And since this is a preparation function, we should not destroy the db. Maybe we should return it instead of database star. And then we need to update our signature. Instead of void prepare, it'll be a database star prepare. And then we're filtering out everything which is not ELF binaries. And let's log that as well. Let's just do %d left. And this is db.num again. Or not, it should be an arrow num. And that is all the preparations we need, I think. So let's return db. version. This is currently 0.1, let's say. And we'll print some simple welcome message. Which is just bird flu antivirus software version and the version. And then we set our db equal to prepare. Then we destroy db and exit. Alright, let's see if this works. That's interesting. Let's try it first on something other than slash. Let's try it on TMP. Alright, bird flu antivirus, enumerating file system found 497 files, filtering out non-executables, 11 left. Okay, so this works as intended, but why does it crash when we run it against slash? Let's see how strace looks. Okay, maybe it has something to do with our length, because we're only allowing 63 characters, but it shouldn't crash because of that. That's weird. What's the last file? This. And how many characters long is that path? 63. Okay, so it has to do with that. But I still don't see why it would crash. So what's really happening here? Well, we do the string copy. Copy the 63 to the entry in the database from the path. And then we add to db in the entry. How does this look inside of GDB? just set up the environment a little bit. And let's create my XX macro as well, which runs x30i against EIP minus 20. And right, let's run this thing. Inside of add directory. And the stack doesn't look too well. I have never seen a push instruction crash before. Is it filling up the entire stack? Is that it? Seems like. Let's see. It starts at 0x. Is it here? I don't really remember. Or is it the BF prefix? Well, easy enough to find out. If we just do start, yes, info reg ESP. Okay, so this is the first position. So this is how many bytes we used on the stack. Yeah, 8 megabytes is the stack size. Okay, so we're filling up the entire stack. Why? Well, this buffer is kind of huge, but not that huge. Well, we do a lot of wait a second. We do a lot of recursive calls, and each function call will need its own stack frame. So maybe when we run out of the buffer, yeah, that's probably it. When we get up to the 63 limit, we keep trying to recurse into the same directory over and over and over again. That's why. So what do we do? Are we going to increase the path size? Well, I guess we are, but that's not really enough. We need to have some kind of protection against this anyhow. So basically we need to do a comparison. If the new path is the same as the old one, then we should not use it. Let's start there. So if string compare tmp and path, that's the name of it, right? Yeah. So if they are the same, no. If they're not the same, then we recurse. Otherwise, we just do nothing, I guess. Let's try if this works. Different signs. TMP and path. TMP is in int 8 and path is in int 8. So we need to make this a char and this a char. Okay, I meant this. The one with an N inside of it is only comparing a specific number of bytes. Okay, that solved it. So if the path is too big, then we just carry on with our business. But it was really, really fast. Maybe it was cached somehow. Found 155,000 files. Filtering the non-executables seems to take a little bit longer. But anyhow, I think we need to increase this size. So we both fix the bug and we better the program. So let's see. The directory should be bigger. Let's say the file is 64 and the directory is 256. And let's search this file for 32. And 31, nothing. If we go here and we search for, I don't want to get hits for int32. So how do I specify that in a regex? Can I do something like, never mind, let's just do, it should not end with a T, then 32. Nothing. 31. So this should be, no, we should start with the other one so we don't collide. So let's search for 64. have this, we have this, we have this now, and 63, nothing. If we go to the C file and we search for 64, this should be 256, 256, and 256. That's all. And let's search for 63. This should be 255, 255, 255, and 255. And let's go over to the other one. So we search for 31. And this will be 63 now. Same here. And that's all. Okay, so now we have increased everything. Okay, so 2,720 executables on the system. And it took a while, but it did not take very, very long. So it seems to be rather effective after all. Let's make this and try again now that we have bigger. Okay, so now we found more files when we increase the path size. And it doesn't crash, so it's looking fine. And that's all the preparations we need. The next logical step is to scan all those executables for viruses. And we need a virus signature database. Did you know that I made a book about computer networking? You will learn how the internet works and how everything works under the hood. It's a complete beginner's course, but it has some advanced elements as well. And you will learn network design and network security and all different kinds of stuff. For more info, check out books.drbirch.com. That is books.drbirch.com. Thank you for your support. Alright, you guys, welcome back. Until we figure out how to grab those virus definitions, let's worry about how we are going to store them. I think the easiest way will be to simply, we can do it like this. Let's say we have a virus definition file. Let's call it what is virus in pluralis? Is it viri, maybe? Dot def for definition, let's say. So each line will contain the specific virus fingerprint, if you will. And this file can have a format such like this. So let's have the virus name first. This will be a comment, by the way. So virus name, and that should be one word. And then it follows a series of hex characters like this. And these hex characters will be translated into the specific fingerprint. So if these bytes are to be found inside of the infected binary, then we have located the virus with this name. All right. So let's see if we can parse such a file. By the way, let's add an example. So let's say example virus, and then we have some fingerprint 5C3301 DD98. That's our fingerprint for example virus, let's say 1. Right? Simple enough. But how do we parse these hex characters and so on? I'm not sure, actually. Let's see what we figure out along the way. So what we need is something which, let's see, I think, shall we translate the file to memory or not? If the virus definition files grows really large, it will be a huge problem if we put it into the memory. In this case, it will probably not be that large, but we do want to obtain the possibility for the future, which means we need to have a self-contained function that parses the file and checks the specific binary for virus. Yeah, that's how we need to work this thing. So let's see how we do this. Are we going to return something from this function? Yes, we are. We are going to return a list of the infected binaries. So we're going to return a database. And this will be called scan. And what does it take as an input? Well, it takes a database of files, right? And it takes a let's see, it takes a file descriptor of the config file or the virus definition file. I think that should do it. So we need to update our database once again, and not only, let's see, well, we need to have a boolean infected. So if it's infected or not, this specific file. That is one thing. Or maybe we should make it a state machine. So if we call this the state instead, and then we define different stages. So let's say we have an enum E state, where the first is unscanned, and the next stage is scanning. Then we have possibly infected, what else? Infected, and what should be the step after infected? Because we can address it in several ways. We can delete file and we might be able to clean it from the virus. So what is a common name for those two? Healed. And after that, it goes back to unscanned. And let's also do a type definition. So we have an enum E state, and we call this, let's see, might want to have an optional argument as well. So let's call this E state with a small e, and then we define a structure which is the S state. And this one contains an E state, which we can call the state. And then we have an argument to this one, because if it is infected, at least we want to save the name of the virus, right? Yeah. So let's just have an int 8 right here. We'll call it virus, and we'll give it a 32-byte identifier. And this one we can type def struct S state as the capital state, so to speak. Right. And we need to zero out the state. I might create a constructor function for this. So state make state, and we don't have any arguments. And we go to here and just create a very simple function. So state make state, and I don't think we need to make this a pointer, right? No. Make state, and we will have a state S. Which is all 0. And we'll set S state equal to unscanned. And we return S. Easy peasy. Right, so when we create this entries for the database, we do that inside of add directory, we also need to set its state. So at this point it is still unscanned, right? By the way, I made a mistake. Let's take a short break. Did you learn anything useful today? And you want to support this channel? Go to drbirch.com/support. You can also click the button Become a Member. Thank you for your support. Alright, welcome back you guys. We can't simply do just like I did up here, because the state is a structure. So we made this in levels, so to speak. So we have this state, and the state has its state. Maybe we should rename this to stage. That is a better way to do it, I think. So the s dot state dot stage is equal to this. All right? Which means that e state dot well, first we need to create it. So e state is equal to make state, like so. And then we set e stage. Well, it's still unscanned at this point. So let it be the default, by the way. And same, well, if you find a directory, it does not need any state, does it? Let's do something like e dot state is equal to make state, like in the other case, but e dot state stage will be equal to unstaged, which basically means that it does not have any state. All right, it's a directory. So unstaged is 0. That's why I like to begin with 1 when I create these, because more often than not you need to insert something in the beginning right here. Unstaged, yeah, sure, why not? Alright, so now I created a state, and our next step is to scan it. So we need to create this scan function. And it takes an input database and it creates an output database. It does also use the file descriptor we give it. So let's start at the other end. Let's see. We prepare the DB. Then we scan. No, then we open the file. So we need an int32fd, and we need an signed int ret. And we does also need a name for the virus database. Let's hard code that for now. So we'll do something like, I'm not sure if we can do this, but let's try. Can we do int8 viri file? No. Virus file. Like this is equal to int 8 casted string. I'm not sure if this works, but let's try it. And this will be dot slash viri.def. So we set our fd, no, we set our ret equal to open, and we open the virus file, and we need to cast this to a char. And we'll open this as o read only. And if our return value is less than 1, we'll print some error, unable to open virus definition file. This virus file. Ah, it just broke. Unable to open virus definitions instead. And then we exit with -1. Otherwise, we will just set our fd equal to the return value. So now we have an open file. Now we can set our db. Maybe we should create a new pointer for this db. Let's call it scan db. So scan db is equal to scan, and we give it the database db and the file descriptor fd. Like so. Maybe we can put the logs here as well. No, I don't want to do that, by the way. We can put one of them. We can put this. Scanning ... like so. Then we scan, and for now, afterwards we'll print something like we do a return, and we print, no, yeah, we do a return, and then this and this, and we print something like scanning done. Then we destroy the DB and quit. Alright, so now to the scan function. How do we parse this thing? We need to be able to read one line at the time, right? So let's just create this function. It will return a new database, and it will be called scan. It takes an old database, let's call this DB, and it takes an int32 file descriptor. So we need to have two loops, one that scans for words and one that scans for lines, I suppose. Or maybe we can do it in one go. We can have some kind of stage here as well. I'm not sure if we can define those things inside of functions, but since we can make functions inside of functions, why shouldn't we? But perhaps not. Let's try. We don't learn unless we try. So let's say we have an enum e. Maybe we can just do enum like this. So we don't have to come up with a nifty enough name. Well, this will also be some kind of a mini state machine. And basically I want to do something like so let's take this in the perspective of what we are looking for. So first we look for a space so we can divide the two words, right? No, we can't do that. We need to first find the end of the line. Otherwise, we don't know how much to read in the second half. So basically, well, look at this. The file looks something like this. virus1 and then hexadecimal numbers, right? And then at the end is a new line. So what we need to do is first go character by character looking for the new line. When we find it, we need to record its position and then go backwards looking for the space. Then we have the first word easily, and we have the second word. But what about the buffering? Because we can only read so many bytes at a time into the buffer. So we need to know when we have reached that point. Because let's say we have like lots of different definitions. And we have a buffer that reads, I don't know, this at the time. So then we are stuck in between stuff. If we only get this in the buffer, how will we handle reading in the rest? It's a bit tricky, actually. But what about if we read into the buffer as much as we can, and if we fill the entire buffer, which basically means that there's more to read, right? So we're probably in between a line. Then we only utilize the stuff that has a full line, so to speak. So this last line we just discard for now. And the next time we read into the buffer, we rewind until we find this new line. Then we jump forward one step, and then we start again. So we need to implement the buffering ourselves as well. Well, this is a low level course after all, right? So why not? So, well, let's do this first. First, when we have a buffer, we look for a new line. Then we rewind, looking for a space. And then we go back to looking for a new line. So we will only be alternating between these two states, I suppose. And this will be our parser, basically. We haven't got an error from VS Code, so maybe this works. And what else then? We need a buffer, and it doesn't really matter how big it is. But I want to make this a little bit dynamic, so let's define a buffer size. And let's keep it low for now so we can easily test this. Let's say 16 bytes. That is the buffer size. So we'll have an int 8 buff of size, buff size. No. I came up with a better solution. Let's do this a little bit more structured. Let's start by creating this stage thing that we had, but in a little better way. So let's call this buff stage, buff state. And we are looking for a new line, that's 1. And then we are looking for a space, that's 2. We type def this to, let's see, enum e buff state. But we will also create a structure which we'll call a buffer. And what is a buffer? Well, it is a file descriptor, FD. It is a buff state. It is an int32. No, maybe we should make it bigger. Will this file exceed 4 gigabytes? Possibly. Let's make it an int64. And this is the position in file where we currently is. So Yeah. And this is the file pos. But we will also have a smaller thing, which is an int 16. Which is an int 8 pointer, I think. And this is the buff pos. So this is position in memory. This is position on the file on disk. And we do a typedef struct s buffer, and we call this a buffer. By the way, we can also store our actual buffer in here. So we'll have an int 8 buff of buff size. Okay, this grew a little bit more complicated than I anticipated, but I think this is the way to do it. So in this file we will have a buffer, buff, which will be equal to all zeros to start with. We can set our FD, because that one we have from the beginning. And just to make everything clear, we'll also set the other ones. So buff state will for now be, well, the first thing we're going to look for is a new line, so let's set that. What else do we have? We have the file position and buff position. Well, the buff file pos is equal to the buff. No, let's just do 0 here. And buff, what do you call it? Buff pos is equal to an int 8 casted 0. Because this will point to the actual place in our buffer. Yeah, I think this is the right way. Yeah, let's do it like this. So what is the first thing we want to do? We want to read one character from this thing. So let's do that. Let's create a simple int 8, which we'll call C. And for now, C will be equal to read byte. And we give it a reference to our buffer as an input. So this will be an input and an output parameter. All right? And save, and we'll be right back after this. All right, welcome back, you guys. Let's continue our work. Last section we started implementing a low-level I/O buffer, and we'll continue to do that. But I need to add a couple of things. I need to add a start and an end position, so we know where we are in the current buffer, so to speak. And I'm not going to do it this way with read byte, I think. Or let's start like that and see where it takes us. So what would this read byte be? Well, it would return a single int 8, and it will take a pointer to our buffer as an argument. And let's also add a state, an idle state that we can start with. So let's change this from new line to idle. And this is going to be real low-level code. I might be overcomplicating things, so maybe we will make it a little bit simpler in the end. But it's still good to know how to do these things, because in some occasions you have to implement a buffer like this, even though it would be possible in this case to maybe do it a little bit easier. Anyhow, let's also set our new things. We have a buff.start, which will be a 0 for now, and a buff.end, which will also be a 0, and we cast it to a int 8. All right, so let's see. Well, let's start from the beginning. If the buff state is equal to idle, so this is precisely at the beginning, then we want to read, right? So we need an signed int ret, and we need an int 32 n. So ret will be equal to read, and we read from the, let's see, we need to take the file descriptor, cast it to an integer, and we also need to, let's see, well, whenever we want to read, we want to erase the buffer first, so let's do that. So we'll zero out buff with buff size, right? And then we will read into the buff, and buff size -1 is the maximum, right? So then we get to get back a return value. If the return value is less than 1, that means either that we have read everything and it's end of file, or that it failed somehow. So in that case, we will return a 0 just to indicate that. Otherwise, we will set our n equal to the return value, or the in32 cast return value. So n now contains the number of bytes read. All right, so what we want to know right now is, did we read the last part of the buffer? Because let's say we are at this position and we read all the bytes in the file. Then we will possibly get less than buffer size minus 1 bytes back. So let's check for that. If n is less than buffer size minus 1, then we have read everything. Let's see how we can indicate that. Maybe we also need to get something like bool end of file. So buff dot end of file is false to begin with, but in this case we will set it to true. So buff end of file equal to true. Right. And what about the other stuff? Now that we have read some bytes, we can calculate the start and the end and stuff like that. So I think I need to copy this whole thing so I have it easily available. Okay, so let's start by setting the buff position. And I think we can do that outside of the if statement. So buff pos should be equal to the beginning of the buffer. So buff in this case. And this should also be like this. And buff start should also be equal to that. So let's do this little trick where we define buff pos is equal to buff start, and that is in turn equal to buff. I think we can do this even with pointers. I'm not entirely sure though, so let's see what happens. Can we calculate the end as well? Yes, we should be able to do that. The end should be equal to the start plus the number of bytes read minus 1, I suppose. Let's see right here. If we are at this position and we have read this line, say, then n will be equal to 1, 2, 3, 4, 5, 6, 7, 8. So if we are at this position and we jump 7 positions to the right, 1, 2, 3, 4, 5, 6, 7. Did I calculate this wrong? Let's see. We have 1, 2, 3, 4, 5, 6, 7, 8. Okay, we have 9 here. So we should jump 8 positions. 1, 2, 3, 4, 5, 6, 7, 8. So 8 is the ending position of the buffer. That is correct, no matter how big n is. So now we have those different things, but we also need to take into account that we might have read like this. So we are in the middle of a line at the end. And how do we know if we are? Well, basically we can check. This is the optimal thing, that we read an end where the line ends. And in that case, the end character will be a new line. So let's check for that. If buff end is equal to new line, then everything is fine, right? And we don't need to do a whole lot more. But if not, okay, this is a little bit ugly. Let's do not equal to. Okay, so if it's not equal to that, then we are basically either at the beginning of the next line, or we're in the middle. In both cases, we want to rewind to here. So we get we want to rewind so we back up to the line above. And how do we do that? We need to, first of all, get to know how where our position in the file is. So let's start there. And there is something called lseek, reposition read write file offset. Offset once. So if we take, let's see. Right, we can use this seeker to get the current location in the file. And since these files are pretty big, we need to make this an int64. But we, by the way, we have one already inside of our structure. So let's just call lseek on our fd, that is buff fd, or rather the integer version of that. And by the way, this is an int8, so we should make this a char. Right, so we have our fd. The next thing is an offset, and we don't need an offset in this case. Just to do 0. And then we have the whence, which is those things. So we want the current position in file. And let's set our ret equal to this. And then we need to check if it failed. If -1, okay. So if ret is -1, then we will return 0 because we can't do much. But it shouldn't fail. Hopefully. So we'll set this to this, and otherwise we will set our buff. What did we call that? File pause. We'll set our file pause equal to ret. Like so. Okay, so now we know our position in file. So let's first check. Now we should be inside of here. Let's first check if our file pause is 0, because then we can't back anywhere. Let's see. If buff file pause is 0, then this shouldn't be dot. Well, in that case, we want to just handle this as if as if we were ending with a new line. So let's do the opposite. We check if file pause is positive, or yeah. And in that case, we want to back up. So we'll do that. Well, we'll do that by taking the file pause and -1. And then we want to set it using lseek. And we'll give our buff fd. And let's see what we have. Seek set. The file offset is set to offset bytes, right? So if we use that, and we give the integer version, or should it be the integer version? Off t. I'm not sure how big an off t is. Let's find out. So I'll just do a simple print f, and I will give size of t. 4. It's just a 32-bit thing. That's a little lame. But it is what it is. Maybe there's another system call which deals with bigger things, but since we don't, we will limit ourselves a little bit. And we will not have a bigger file than 4 gigabytes for now. Right, so then we can actually do this. And we give the buff file pause, and we do seek set instead. So now we have backed up one step in the file. So if we were here before, now we are here. And if we were to read 1 byte now, we would get this one, right? And then it would increase. So we would be back at the same position. So we need to back up again afterwards. Right, so we need a temporary buffer. Let's do this, int 8, tmp. It doesn't need to be bigger than 2 bytes. And I don't want to make a function call to 0, so I will just zero it out myself. tmp will be equal to integer 0, no, this kind of 0. And tmp plus 1, same thing. And now we also need to check that the ret didn't fail. So if return value is not -1, we'll do this. Okay, so ret is equal to read from the buff file from the integer version of buff fd, and we read into tmp, and we read 1 byte. And we need to check again if ret, it would be a lot of nested if statements here, which I don't really like. But we need to do it like that because if anything of these steps fail, we still want to continue with our other stuff. So we'll just check if ret is equal to 1. We'll continue. And in that case, we need to check the contents of that buffer. So if tmp is not equal to a new line still, then we want to redo this thing. So let's say we back up one step again. So we can take those 3 lines. We decrease the file paths. We set it. We check that we are not in an error case. And then we just continue. But if we have found our new line at this point, then we are done. So now we need to update our other things. Maybe we should have some kind of counter so we know how many bytes we have backed up. So in the beginning, we will set x equal to 0. And every time that we, let's see, every time we do this and get a 1 back, we will increase x. So we know how many times we have backed up. Because now we can take the buff end position and update it that many bytes. Let's also 0 buff end. No, buff, let's see. Yes, buff end. And we want to 0 out x number of bytes. So if we have read this, we back up to the new line right here, and inside the buffer those bytes are still there, so we 0 out those bytes. So now we are at this ending position. And we need to loop as well. So instead of if, we can make this a while. So all of this will loop until we find this new line thing. Very complicated code, but I think it will work. Maybe some weird thing somewhere that we need to fix. But it will make our lives a lot easier later on if we know that we always have just whole lines in our buffer. Okay, so now we have done that. So after this while loop, we have a buffer which we can deal with. Let's see, and all this happens if we're in an idle state. So the next step is to, let's see, where we have one too few, I guess. Where do we? Here, I suppose. No? Let's see, where did we open something and didn't close it? Here we have this. Here. Let's do that. Alright, so if we select this, we are all the way down here. If n is less than buff size minus 1, that should be after. And at this point, we don't want to idle any longer. So we'll set buff state equal to new line, because that is the first thing we want to look for. So let's do that. But we only want to change state if we are inside of the idle state. So this should actually be inside of here. So let's do another if statement. If buff state is equal to new line, and what do we want to do if it's equal to new line? Well, let's set our starting position at this point, or a current position, buff pos, equal to the end. So, because no, we are looking for the first new line. Let's not do that. And this whole function is only going to return 1 byte. So maybe we don't need to do a whole lot more. We need to have a variable for the thing which is going to return. So let's say int 8c. And it doesn't matter if we're looking for a new line or if we're looking for the space. In both those cases, we want to set c equal to what the current position of buff pos is. But if we are looking for a new line, we want to back up one step. So buff pos will basically be the thing that we're going to read next. I'm not sure if I like that. No, I don't. Let's remove this and let's make this an else if statement instead. So if we are looking for a new line and we haven't been in the idle state in this function call, we want to first check if buff pause is equal to buff start, because then we can't back up anymore. I'm going in the wrong direction. When we look at a new line, we go to the right. So if buff pos is equal to the end position, then we can't go any further. So then we have to return 0 to indicate an error. Otherwise, we will take the buff pos and increase it. Set C equal to whatever it points to. And we return C. And if we are looking for a space, we'll basically do the same, but the other way around. We'll check if buff pos is equal to buff start. Then we can't back up anymore. So we need to return 0 to indicate that. Otherwise, we will -1 for the buff pos. Set C equal to whatever it points to. And return C. And these are the 3 possible scenarios. But what about this thing? If we are in the end of file scenario, let's take this thing and put it up a little bit higher. So let's do it here maybe. So we know that this is the last buff. And that we need to take that into account when we are looking for the new line, right? Or maybe we deal with it the same way anyway. Let's see how this goes. So this whole function with all the buffering and stuff will only return 1 byte that we read. So we have read 1 byte. If C is equal to the new line and buff state is equal to new line. So we look for a new line and we find a new line. What do we want to do? Basically, we want to record this position, right? Or no, actually not. All we need to do is to set buff pos value to 0, because then we can copy it easily later on. And we want to change the state, because we have found our new line. Now we want to back up and find our space. Otherwise, if C is equal to space and we are looking for space, what do we want to do in this case? So now we know our new line, we know our space. Maybe we should create variables for these two things. So the first thing is the virus name, and I don't really remember what we set the limit to be for that name. Entry here. $32, okay. And we also need one for the fingerprint, and that can be longer. How long? Well, we need to decide. Let's say buff size long. Okay, so at this point we know our things. We know where the new line is, we know where space is. So if we do the same, we set buff pos equal to 0, and then we copy, let's 0 it first. We 0 the let's start with the fingerprint buff size. So we copy from buff pos plus 1, so one step after the space. And how much do we want to copy? We want to copy until the end, right? So that would be the integer of buff end minus buff end minus buff pos. I think we need to check an example for this. So let's see. If we are at this position, and this is the end, and this has been replaced with a 0 like this. We have a R here and start copying from here. So it will be the end position minus the buff position minus 1. Minus 1. And before that we need to put our, let's see, this is our destination, so we need our, no, let's see, this is our source. So we need our destination first, and that is our fingerprint. Buff pause plus 1. Let's do this. Cheat a little bit. Okay, so now we have copied our fingerprint. Now we want to do the same for the virus name. So we want to string copy into our virus, but first we want to 0 the virus 32. We copy to the virus. And what do we copy? We want to copy from buff from the start. And all the way to the, let's see, all the way to the 0 that we have put there. So we can actually copy maximum, and we can actually do the same here. So let's say buff size minus 1 here instead. And now we have the two definitions. Now we need to change our buff pause to be equal to what actually? We wanted to go past the 0. And we didn't record where the line ended. Shall we do that? Maybe. Yeah, it will make our lives a little bit easier, so let's do it. So basically, when we are looking for a new line, and we find it up here, then we will set our buff, let's say end of line, to be equal to our current position. We need to add this thing as well. So int 8 end of line. And for our constructor, it will be set to a 0 like the other ones. So at this point, we can simply set this equal to buff end of line plus 1. So then we can continue to find the next thing. And what will be our state in this case? Well, it will, well, what would it be? It depends, I guess. Because if the new buff position is equal to the end then we want to check if we are at the end of file, and in that case we want to be done basically. So let's do return something, and we'll figure out what the something is later on. But otherwise we want to set the buff state equal to idle, so we read in more bytes. And that's only if we're at the end. But we go one past as well. So we need to do less than or equal. Or not even that, only bigger than. And if we are not at the end, we will just carry on with our business. But we want to set the state equal to the next thing we're going to look for is another new line, so we'll set it to that. Okay, a lot of moving parts. But I think we are rather okay. And at this point, before we start increasing and decreasing our variables, we want to scan for this thing. And what exactly do we want to scan? We want to scan all our files for this specific virus. Yeah, I guess we shall. Let's, by the way, create something like database output. And at the beginning we'll set output equal to make database. And I think we need a short break. We'll be right back. Sup guys, welcome back. So where were we? We had implemented our low-level I/O buffer. We haven't yet tested it though. So maybe we should start in that end. Let's see. Let's for now let this function just return its input for the time being. And what are we going to do? Let's just print the name of the virus and the name of the or the contents of the other string. So let's see. We'll do something like this, virus. And then we'll print the fingerprint the same way. So we have the char version of the virus, and we have the char version of the fingerprint. And let's end with a double new line, so we get a little bit of separation between the different fields. Alright, so we print out that virus name, and then we continue on with our business. So let's also call this function. We give it a database and a DB and a FD. And it seems like we are already doing pretty much that. Maybe we should comment this out for the time being. Alright, so let's see if this compiles. This is a very messy function, so I don't think it will compile, but I hope after we have fixed all the bugs that GCC is reporting, I hope it will work then, because if not, this will be very difficult to troubleshoot. Well, let's see. My terminal seems to be a little bit off. Now it works. Alright, so we make clean, jump down a little bit, clear the screen, we run make, and boom! 2 screens of errors. Don't we love it? 3 screens. Alright, let's start at the beginning, as usual. It does not have a state number. Let's see, line 7. Okay, so when we make a state, it does not have one of those. Right, because a state in itself, we should probably not have this state thing here, because the S is the state, right? think that is the problem. Okay, one error out of like 30 fixed. But I still prefer the errors that GCC is reporting me because at least we know where to edit stuff. Alright, buff is a pointer. Did you mean to use the arrow? Yes, I did. Line number 244. Buff arrow state is equal to idle. Alright. Next in line. Buff is a pointer. Did you mean to use the arrow? Yes, I did there as well. Quite funny though, since GCC is apparently able to see the difference between a dot and an arrow when we are accessing those fields, why do we have to specify one or another? That's a philosophical question, right? Alright, so let's see. Assignment to int8, blah blah blah, makes integer from pointer. Right, because $1 is a macro creating a pointer, and in this case we don't want to do that. So 271. So we can't use our macros here because I don't have any for a regular int8. So let's just cast this manually, and this as well. And the rest is fine, I think. Let's see, conflicting types for scan. Database star, database star. What do we have? 313. So database scan in 32. Ah, we did not make this a pointer, but we should. Alright, 1/3 done. Invalid type of have buffer. Right, so here we went in the other wrong direction. In this case, we are not dealing with a pointer, so buff should be using a dot. And we have a lot of these. Let's change them all. So we search for buff. We change this. And this. Put this as well. And we need to change this and this. A lot of these arrows. I could make some search and replace, but we are almost done. Alright, there we go. This probably took away a lot of the errors. Yes, we are down to one screen. Almost. Let's see. Passing argument 1 of 0 for incompatible type that is true. We need to cast this to a, let's see, fingerprint. Made it an int. It should be an int 8. Same here. Weird that I did the same error twice. Alright, let's see what we have left. Okay, down to one screen in 5 minutes. So don't be afraid when you get like 3 screens of errors. It's usually quite quick to fix. Pointer targets differ in signedness 341. Yes, it does. This needs to be cast to a char. Like so. Something is undeclared. Yes, it is. It's very much so. 348. Return something. Let's do this. So or maybe I have a better way. Let's return the input for now, and then I select this like so. And how did I do that? I use a very, very nifty add-on to VS Code, which is called Bookmark. And it's not my extension, and I'm not like, they are not paying me for this, but I like it very much, so I want to show you this one by Alessandro Fragnini. Sorry for the pronunciation. So first of all, you need to enable this extension, and then you need to add this to your configuration. So basically you go into the settings, you go to the command palette, and you select let's see, preferences, open user settings, and you go down here and you put these 3 lines here, and it needs to be top level. And then you can just add a key binding to Control B or something, and it will select that line, and you can select multiple lines. And it will also remember it when you close the file and open it again or restart VS Code, which makes it a very good way to select something that you want, that you need to change later on, or if there's some function that you need to return to several times in a big file, you can select it and it will be easy enough to browse to. Very nifty thing. Alright, so now we return the input, and this is temporary, as you might imagine. Output set but not used. I don't care about that right now. Invalid initializer. Okay, I was a little bit wary about this one. 365. I think I mentioned that. I was not sure if we could do this in one go. My cat is, yeah, sounding. And we couldn't, unfortunately. And we probably can't do this either, right? Huh, it went through. Nice. Warning, variable scan db, set but not used. Control reaches end of non-void function, 311. That's a little bit more. Okay, so if we go down here, we are probably in an error state. Or maybe it could be that the last line in the file does not contain a new line. Let's for now return an error in this case. And maybe we come back to that later on. Which reminds me, I need to check for errors. So if we don't have a C, let's for now output an error. And exit. Later on we'll do something other than that. Alright, so now I believe it should compile at least. Yes, but will it actually be able to parse the file? It was a very messy function, as I mentioned, so I'm maybe 50% sure that it will work, but perhaps less. So it's scanning, but it should not take this long. Sounds a little bit like an endless loop. How does the file look? Okay, it looks like this. We need to add something which removes commented lines, by the way, but that's for another day. Let's copy this thing, remove this, and add those. And we need to have a real new line and not this one. So this is how the file should look. Will that make a difference? No. Okay, so what is the scan function currently doing exactly? It's creating a new database and a buffer and zeroing everything. We're trying to read 1 byte. We check if that byte is a new line, if we're looking for a new line. We check if it's a space, if we're looking for a space. and in other cases we return. So we are not able to read the first byte, basically, because we are not looping here. We are only returning if for now. So let's go to that function and let's think what happens at the first go. We open the file. If buff state is idle, which it is from the beginning, then we zero out our buffer. We read 1 byte. No, we read buff size minus 1 byte. And if it fails, we return 0, which we don't. So n is equal to the return value, which is probably the size of the buffer, I suppose. How big did we set it to? 16. And how big is the file? 187. Okay, so it should make several goes. Let's see. If n is less than the buff size, then we set end of file, which we probably don't. We check where we are inside of the file, which should be about 16 characters in. So let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We don't pass the first line. That could possibly be it. What if we just were to double the buffer? Then we should be able to read the first line at least. Will it make a difference? Nope. And if we trace this, what happens? Obviously a loop. But what is looping? Okay. No, wait a second. This is probably yeah, this is part of the scan. Maybe, is it possible to disable that temporarily without affecting too much stuff? Let's see. Prepare. What does prepare do exactly? It creates a database. It adds the stuff. Let's just do this for now, to make it a little bit easier to watch what's happening. Okay, it does a lot of negative else-seeks. And if we check it a little bit closer, let's see. Okay, so we read the first line and a little bit more. Then we else-seek to position 0 in the file, which is correct, right? Because we want to go to the first. No, this else-seek is checking the current position. And the current position is 31. So then we change it to 30. So we are backing up, right? And how many bytes did we get more than the new line? We have 1, 2, 3, 4, 5, and then the new line. So we back up to S, R, V, A. Okay, so it successfully does what it's supposed to, but it jumps 2 steps every time. So it misses the new line, and that's why it never terminates. So I calculated a little bit wrong. Let's see. Okay, so we are here. If it's not a new line, we decrease the file pause. What if we just comment those 2 out? Well, and those as well. We'll try again. Okay, let's see what happens. Right, so we're back from S to U to R. This time we are doing the right thing at least. To I to V to the new line. And then we do something else. Then we zero out the rest. That's probably this, right? Which is correct. But then what happens? We else-seek again with a 0. Let's see. So if it's 1 at the end, then we check current 1. But that's not what we're doing here. We are changing the position in the file to number 24. And before it was 31, so it's 7 less. And we have 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So it's at the end position here. And that should be fine, I guess. And then we check the current position in file. No, we read. We read an 8. So we keep doing what we did before. Why is this not working? Maybe my wireless is not as reliable as I had hoped. Well, let's do duplicate session. Until 32. Reattach to my screen. Let's close this one. So we are still doing those L6 and stuff. Is that really what we're supposed to? Let's see. If the return value is 1, and if it's not a new line, then we do this. But what if it is a new line? Then we should do this. We set the end to the thing minus x. We zero it out. Okay, so this is what we did. But we are not breaking out of the loop, which we should. So let's do that. I hope this is all there is. So let's see. Okay. Progress, at least. So what are we doing here? We are backing up to the new line, zeroing it out, and then we get the error. Okay, so we break out of the loop, which will land us, let's see, blue one down here, which means the state will be new line, and then, okay, then we reach here. I think, let's see, we do an else if buff plus position equals and return 0. Otherwise, do this. What if we weren't using else if here, but just a regular if statement? Would that work? Let's try. Okay. What really happened there? Exits, just like that. So we back up to the new line, 0, and then we exit. Okay. So we read this thing, none of these apply, and then we return and we exit. Okay, so it's doing what it's supposed to, as of now at least. Maybe we should do something like, let's change this for the time being to just a double new line. And if we don't get an error from our read byte, we will log the character that we read. And a space. And instead of returning down here, we want to loop. Yeah. So let's do something like this for now. Or rather this. And we take all of this stuff, move it out. And we let it loop. And we'll see what happens. We can't use that macro like that because it's a two-line macro. Wrong syntax. This is more correct. Expected expression. Right, we need to have the argument as well. And that is the C. Now it should compile at least. But will it work? Let's see. Okay, so this is what it reads. Example virus. And a space. And then a couple of different of these. But how many of these? DD9. Okay, so we go here. And then we error. We're getting closer, guys. Step by step. That is how coding is supposed to work. Alright, so let's see. Buff, plus. Okay, we can't really do this. Because in the regular case, we want to increase and then read or and return. But in this case, we just want to read. So let's do that. We set C equal to buff pause, return C. So now we should get, because we didn't get the E, right? We did get example, but not the E, and we need that. But the error that happens when we have read almost the whole line, I wonder what that is. So if we're let's see. So we go through this. We are still looking for a new line. Okay, so if it's already at the end, we return 0. But that's not really what we want, because then we don't do anything with the last character. So I think we need to do this actually. Let's try again. Okay, this time we got the E. But we still go to D9 and then error out. D9, is that the end of it? No, there should be an 8 as well. What's up, guys? Welcome back to this section. So, where were we? We were troubleshooting why it stops when it... let's see if I can find the code. It stops when it's about to read the last character on the line. So I think this is the position where it stops. So let's add a little bit of debugging information. So what are the interesting things? Well, the buff position and the buff end are interesting. So let's log buff pos. And this will be buff pos. Like so. And let's paste that in. And then what else do we have? We have the buff end. And let's also log the state. So buff state. Okay. So when it returns 0, it should produce this stuff. Let's also add an extra new line just to be sure. All right, let's compile this thing. Oh, that was a couple of errors. Right, we are interested in the pointer address. Well, this should contain the address. Maybe we just need to cast this. Let's try this. Right. This is just called end. Okay, so now it compiled. Let's see what it says. It still gives us the error, but we don't get any output. So this is not the place where it stops. Where else do we have to return 0? Well, here. But can our else-seek really cause this? And if read fails, we get the same thing. But we shouldn't get into the idle state, right? If buff pause is more than buff end, return the GB. Otherwise, we set it to idle again. But this is only when we have actually found something and printed it out. So this is not the place either. If we search this thing for return 0, we only get stuff inside of the idle parts, except for this. Well, we have this too, but this is when we are in the space state, which we kinda are. Maybe. Let's do the same. Let's copy these things and paste them here. And let's see if we get any wiser. But we need to add one thing though. Since we are looking for the buff start value here, we should add that as well. So buff start. All right, let's see what happens. Still only that error. What if we were to do an L trace on this thing? Well, it begins to write. Let's see. What is this? F right. Okay, that's just because we are writing to the standard error, I suppose. I guess it's the address of the file descriptor or something like that. Well, this didn't give us much. Let's do an strace. And this doesn't make us a whole lot wiser. We do have a return 0 at the end, though. The end that should never be reached, right? Or should it? If it's in the idle and then it goes to the new line state, and the space state. Well, let's do the same. Let's see if we get something. We still don't get anything. Is it updating? Seems like weird. If we don't have a C, we print this error and exit. And that's the only way, the only position where we do that. So it must return 0. Wait a minute. 0, buff, and X. Shouldn't we change state at this point when we have backed up? Well, let's try it. So we have the buff state, and it should go to new line. Let's see what happens. Still nothing. Could it be that C contains a 0? Well, let's do something like this. Mhm. And let's put it here, and we do something like if C, and we log these things, and we do this at every point where we are about to return a C. All right, let's see if it makes us any wiser. Okay, finally we got something. So the buffer starts at this address, the buffer ends at this address, and we are at the end. And this one is the state that we're in. So let's see what it means. New line is the state. And then we print an error. But why do we get a 0 byte? Right, the other function are working against us. Because in this function, we are replacing new line with a 0. So we can copy it a little bit easier. So basically we need to handle finding a 0 when we are in the new line mode as it would be the same as finding a new line, I guess. What exactly do we do if we find a new line? Do we even check for that inside of this function? No, we do only return the byte. So inside of our scan, when we find the new line, so this is it, we set it to 0, and then we change state to space. So why aren't we in the space? Well, let's see. It returns the new line. What then? Does it move? Let's see what we did. So we are in the new line state. We are increasing the position. We are returning whatever's there, which should be the new line in this case. Then we go back to the other function. We check if it's a new line, and if we're in that state, which we are, then we do this, and we should change the state as well. What is this? Buff end of line is equal to buff position. Right, we are recording where the line ends. So then we go back to the beginning of the loop and we read a byte. But why does it say that we are in the new line state? Or did it? Yes, I think it did. 1, 1. Because if it happens in this order that I just mentioned, then we should have changed state before we print anything. Well, I told you, didn't I, that this would be a mess to troubleshoot. But I think if we get this part to work, the rest will just work, I hope. We always read from the buff pos after we have increased or decreased. So if we change stuff at the buff pos like we are, let's see if this code is triggered. Because it might read a 0 for some other reason, and then we are troubleshooting the wrong thing. Nope, it's not triggered. Can it be this? But it seems to be in the wrong place. But let's try. Nope, not there either. So why would it read a 0 from an ASCII file? Why would it do that? Because we haven't added any zeros. Then we would have triggered that code. What's this red thing, by the way? Yeah, that's not it. We need to somehow differentiate between those different logs. Let's do a capital B on this one. And this we have tried. We do a capital S here. And let's do capital buff end here. So we know where we are, so to speak. Okay, we got a big S. So we are here. This is the last thing that happens. So if we are in the new line state, and if buff position is bigger than end, we would have done this, but we don't. Instead, we are increasing the buff position. We're setting C to that. And C is 0. And we have the 9 as the last thing. Well, we should have an 8 here, shouldn't we? Maybe we are overriding it. Let's print the entire buffer. So that'll be buff. Let's see what we got. Okay, so we have the example virus, but only the 9. We are overwriting the 8, and that's why it's such a weird bug. Alright, so where are we overriding stuff? Must be right here. So instead of doing minus x, let's do x plus 1, I suppose. No, that's wrong. We should do buff end plus 1, of course. And maybe we should do minus 1 here instead then, so we don't go too far. Okay, let's see what happens. I'm feeling a little bit optimistic, I must say. Oh, would you look at that? Let's remove all of those logs. So we can see things a little bit clearer. Let's remove this part and this whole if statement and all this. Alright, so now we should be able to see a little bit better. Okay, So we get a couple of fingerprints. Virus. We do get it. The stuff that's printed here, that's only because of this scan. Where are we? This. Let's remove this. And maybe this works now. Let's try it again. Virus, example virus, virus 1, virus 2. All of these things are the same though, but I think that is because they are in the file. Right, they are. And the first one should be different. And it is. Unbelievable. We got this thing to work. It concludes with an error though. And it goes to virus 8. How big is this file? Well, virus 8 is the last thing. If we go up a little bit before we deleted the logs. Okay, so we are in the state of new line. We're at this position one step after the end. Buffer still contains virus 8. Which means that the buff position, no, it does not mean that, but the start position is at the V, beginning of the line. So it doesn't handle the end of file correctly, which should be easy enough to fix, I suppose. Or maybe we don't need to, because actually when the file has ended, we sure can return a 0. We just don't need to interpret that as an error. We can interpret it as we are done. Let's do that. Instead of this and this and this, we will just return db for now. And now, ladies and gentlemen, when we run this thing, it works. 100,000%. What do you say about that, huh? We have successfully developed a low-level I/O buffer. Kinda neat. And this is currently very specialized to what we are doing with the reading of the configuration file with a space and the new lines and stuff. But I think it would be quite possible, perhaps even easy, to generalize this so we can use it for reading any file. Maybe even reading other stuff like network communication and intra-process communication, perhaps communication with the kernel. I don't know, but very cool. So how are we going to use this thing? Well, we want to take the fingerprint and we need to turn it from ASCII into real hexadecimal bytes. Right. So let's do that. Um, so let's think about this. How can we go from hexadecimal to from ASCII to hexadecimal? We need to first check. Let's see. If we print out a 0, the ASCII 0, and we pipe this to hexdump, we get 30. And 1 is just 31, yes, and it goes up all the way to 9. So that's our one case. So basically, if we take whatever we have here, as long as it's between 0 and 9, then we can just do minus 30 in hexadecimal, and we get the correct one. So let's start there. I think we're going to do some of this stuff as a macro. So let's define a macro. Let's call it ASCII to hexadecimal, perhaps. And what are we going to check for? Well, we're going to have an argument, wouldn't we? We're going to have an x. And let's see. If our x, a lot of parentheses again, if our x is more than 29, no, 20f is the one before 30, and x is less than 3a. So then we are dealing with the digits between 0 and 9. In that case, we want to return x minus hexadecimal 30. Otherwise, we assume we are dealing with or maybe we shouldn't assume. Let's see what an A is. 61 and F is 66. So if our x is more than 60 and our x is less than 67, so then we are dealing with hexadecimals. And we want the A to become 10. So 10 plus something should be 61. So basically we should do 61 minus 10. 87, and 87 in hex is 5, 7. Let's double check that I'm correct about this. So let's say we have an F which is 66, and we minus 57, then we get a 15, and that is correct. So we take minus 57 hex. So we have x minus 57. And if we have another case, then we should just return 0. Right? And we are only having support for lowercase characters. I don't want to make this even messier. So let's try this thing. If we go down to our main, we can just do something like let's see, we want to print the hexadecimal value of, and this should be a byte, by the way, so HHX. And we do ASCII to hex, and we give it the character E. And then we exit. So if this works, we should get a 14, right? Or in hex, we should get an E, rather. Maybe we should do .02 as well. So we only get 2 digits. We got an E. Very nice. And what if we have a 5 instead? And let's print that as a regular integer for convenience. Or no, let's not. We got ourselves a 5. Okay, so now we can handle one single character, but if we look at our virus definitions, we have 2 for each byte. So we need to add those together somehow. And I don't want to do that inside of a macro, but we can create a simple function, I suppose. So let's say we have a function which returns one single int8 character or digit. and let's call this ASCII to hex, and we will take a string as input, so basically an int8 pointer. Because we need 2 characters, right? Yeah, let's do it like that. So let's go up here and we define this function. So int8 ASCII to hex, and we take an int8 pointer, which is string, let's say, and let's assert that let's assert that the 3rd character is a 0, which basically means that that the length of this string is 2, without having to call string length or anything like that. Alright, so what do we need? We need 2 int8s, A and B. And if we look at this in hex, we will have the A and we will have the B. And we need to mash those together into a resulting int8. So let's start with A. A is equal to 1st character, B is equal to the 2nd, and result should be equal to let's see, the A, but pushed 4 bits to the left. Because if we look at this in hex, I mean in binary, we want A, B, B, B. If each of these are zeros or ones. So basically we take the A's and push them 4 bits to the left. So then we are left with this. And then we should just be able to OR the B. I think this is correct. And then we return res. But by the way, A is not equal to this. It is actually equal to A to H, this. Because we need to translate from those ASCII characters with the help of our macro. Alright, I think this is it. So let's try this out, ASCII to hex. Let's define string, let's call it hex like this, and it should be equal to, I don't know, something that we can easily verify. C8. And what do we want to do? We want to print out, let's see, we want to call ASCII to hex, and we want to give it our string, and hopefully we'll get back the same thing, C8. Let's see if we do. C8, will you look at that? Kind of nice, huh? So now we only need to parse that string of characters, translate it into real hexadecimal bytes, and put it inside of an array or something. So let's make a function for that as well. So let's see, we want to return a string of bytes. And what are we going to call this? Parse. It's too long. Parse FP, fingerprint. Parse hex. And what is our input? That is a string of ASCII things. So how do we do this? And should it be null terminated? Yes, it should be double null terminated even, to make this simpler. So let's see. We need an output as well. Let's call it ret for return value. And how much do we need to allocate? Well, we need to find that out first. So we need to count how many pairs of 2 hexadecimal characters we got. That's easy enough. We'll do a for loop where we set p equal to str. We're going to loop as long as we have a p, and at each iteration p should be plus equal to. So we jump 2 steps at a time. And we need a counter in 16n. We'll set n to 0, and n will increase 1 step at each iteration. And that's all, I guess. Now n should contain our number of bytes. Number of pairs, actually. So now we can allocate. And how much do we want to allocate? Maybe we should create size for this. So size is equal to n plus 1, let's say. And ret should be equal to malloc size. And let's assert that we have a ret. And let's zero our ret by size. And now we do a new for loop where we set p is equal to str again. We'll loop as long as we have a p, and p should plus equals 2. At each iteration, what are we going to do? We need an intermediate buffer of 3 bytes. So let's clear out that buffer and let's set the first should be equal to p, and the second should be equal to p plus 1. So that is our input. We need something to take care of the output as well. Let's see. Yeah, it returns an int 8 right on. So let's see. We need to have a pointer which is following our return as well. So let's call this a ret pointer. And we'll set the ret pointer equal to ret. And same principle. We should increase the ret pointer, but only by 1. Because 2 ASCII bytes will become 1 single byte. So basically, whatever, and no, I did a stupid mistake which would have been terrible to troubleshoot. The ret pointer should increase, not the ret itself. Glad I found that. So at the position of the ret pointer, we want to call ASCII to hex, and we'll give it our intermediate value, buff. So then we write it to this buffer. And that's it. And we can return ret. Alright. So let's try this on one of the fingerprints. So let's see, where do we have those? We have our virus definition file. Let's go, let's add a signature for this one as well. So this is an int 8 star. parse hex, and we give it an int 8 star. So let's say we have this and double the null terminator. And how can we print this? Well, let's just print the first 32 bits. So if we create an int 8 star p, let's see. Let's do p and hex. And hex should be equal to parse hex. Okay, we already named it hex. Hexes. Several hex. But we should give it single hex. And then we point our p towards this hex. And let's print out the hexadecimal value of p dereferenced. So the first 4 bytes of the returned string as a hexadecimal integer. Okay, we got ourselves some errors. Assignment to expression with array type. Right, this should be hexes. And this should also be hexes. Well, one should never name variables too similarly. Let's see if this works. If this works, however, we should get 5C3301DD. Perhaps it will print in the reverse order, but we will get this stuff. It did only print 5C. Right, we should not make this an int 8. I think we need to go around the, what is the saying? We have to go around the river for water. By doing something like this, let's create an int 32p, and then we also need a void pointer in between. Let's call it mem. So we set mem equal to this, and we set p equal to mem. Okay, we got something. So we have the 5C 3301 DD, and that is exactly the first 32 bits of this. It is printed in reverse order because this is a little endian system, and when we interpret it not as a string but as a regular integer, it will become like this. But we will treat it as a string, so that's no problem. It works. Everything works. Isn't it wonderful? How often does that happen? Can barely remember the last time. I think this is a good enough place to stop, actually. We have successfully implemented a low-level I/O buffer and a hex parser. So if you like this episode, please like and subscribe. And there will be more to this series and other series. So thank you for watching, and thanks for today.